we're going to start with molecular compounds. Before we do that, we're going to determine the number of electrons in an atom. So if the atom has a neutral charge, we look at the atomic number. So if an atom has a neutral charge, the protons equals electrons. Use the atomic number. That's this number right up here. That's the atomic number. If an atom is ionic, well, then we go to the periodic table of ions. Use periodic table of ions. Positive charged ions have lost electrons. Negative charged gained electrons. All right, so we look here at our periodic table of ions. You can see hydrogen has a 1+ charge, lithium is a 1+. So normally hydrogen has 1 electron because its atomic number is 1. Now because it's got a 1+ charge, it's lost an electron and has 0 electrons. Lithium normally has 3 electrons, but it's got a 1+ charge, so it's lost 1. So now it's got 2 electrons. You can see the first group here is all +1s. This is all +2s. This is all +3 charges, mostly +4s, mostly +5s, and then it gets all confusing in here until you get way over to here. And these guys, these are -3s, -2s, -1s, no minuses. So it's kind of normal here for the first bit. Until you get to the transition metals, then it's all chaos. Then it's normal over here for the molecular negatively charged items. Right, everyone in this column is -1, -2, -3. All right, we'll work on that. So covalent bonds. Molecular compounds are generally 2 non-metals. Molecular compounds, 2 guys from this staircase here. Normally, noble gases don't bond with anything. Normally. These guys here bond with each other using covalent bonds. Covalent bonds. A covalent bond is a shared pair of electrons. That's what it is. These electrons are called bonding pairs. Right, so when 2 things are covalently bonded, they will share a pair of electrons. Now we can write it like this. So here's H2. So this is H2, hydrogen gas. They have 1 shared pair of electrons. Or we can draw it out like this, where 1 bar represents a shared pair. All right, so each atom can have electron in electron shells. I don't know what word goes in here. That word makes sense without it. Each shell can hold 2n² electrons. we could put numerous electron shells. So each shell can hold 2 n squared. That means the first shell can hold, so shell 1 can hold 1 electron. Shell 2 can hold 8 electrons. 2 electrons. 8 electrons. Shell 3 can hold 18 electrons. Shell 4 can hold 32 electrons. Shell 5 can hold 50 electrons. Now, practically speaking, once you get to 32, 32 is the most number of electrons you find in any electron shell bigger. Even though a shell 5 could, in theory, hold more than 32 electrons, it only holds 32. Now, however, only valence electrons are used for bonding. We call these valence, they're the outermost electrons. The first shell can hold 2 valence electrons. Each subsequent shell can hold 8 valence electrons. So even this guy out here that has 18, its valence only has 8. Its last shell. Now, here's the rule. Molecular compounds want full valence shells. Molecular compounds want full valence shells. Sometimes there's not enough electrons to fill the valence shells, so they have to share them to fill up. So bonding pairs are 2 electrons shared by 2 atoms. Lone pairs are 2 electrons exclusively with 1 atom. All right, so we're going to work our way through Lewis dot diagrams for some of these things. These are kind of confusing, but we'll work through a few. All right, so methane and water. We're going to do Lewis dot diagrams for methane and water. So methane, CH4. Two things that we can know is we can know how many valence electrons we have in total, and we can know how many valence electrons they need in total. So our carbon and our 4 hydrogens. Ugh, that's terrible. Carbon and 4 hydrogens. So each hydrogen has 1 electron. In its valence shell. Carbon has 6 electrons here. Okay, so carbon has 6 electrons. So carbon, there's the nucleus, there's the first electron shell, here's the second electron shell. Carbon has 2 electrons in the first shell, and 1, 2, 3, 4. 4 electrons in the valence shell, the outermost, so 4 electrons. So we have a total of 8 electrons to work with. But how many electrons do they want in their valence shell? Carbon wants 8 electrons in its valence shell. Hydrogen wants 2 electrons in its valence shell. Each hydrogen wants 2 electrons in its valence shell. So we want to have 16 electrons. How can 8 electrons fill up 16 spots in the valence shell? Well, they do that by sharing. This hydrogen is going to share 1 electron with this carbon. This hydrogen is going to share 1 electron with this carbon. This hydrogen is going to share one electron with this carbon. This hydrogen is going to share one electron with this carbon. So when we're drawing a Lewis dot diagram, we put the carbon in the middle. I think it's because it's the least electronegative. I'm going to have to figure that out. So we put the carbon in the middle. We put the hydrogens around it. Okay. And we kind of evenly space them out because there's 4 places for bonding pairs. There's a space for 2 electrons here, a space for 2 electrons here, 2 electrons here, 2 electrons here. Now, carbon needs 8 electrons in its shell. So, or carbon, I should have done carbon in purple. Carbon gets its 4 electrons. And this electron is shared, this electron right here is shared between this carbon and this hydrogen. This electron is shared between this carbon and this hydrogen. Each hydrogen has an electron. This electron gets shared between this hydrogen and this carbon. This electron gets shared between this hydrogen and this carbon. Now, if we look here at this hydrogen gets these 2 electrons. It has a full valence shell. This hydrogen gets these 2 electrons. It has a full valence shell. This hydrogen gets these 2 electrons. It has a full valence shell. And this hydrogen gets these 2 electrons. It has a full valence shell. Carbon gets all 8 of these electrons. So it also has a full valence shell. Every one of these electrons was shared. So our proper Lewis dot diagram for this is C, H, 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 dot, 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 dot. 8 electrons in the valence shell, but they're occupying all 16 slots because they're being shared around. We'll do water in a little bit. Let's try carbon dioxide. Carbon dioxide is CO2. So we know our carbon has 4 electrons in its valence shell. Oxygen has 6 electrons in its valence shell. Right? Oxygen would have 8 electrons, and 2 would go in the first shell. That means 6 would be in the valence shell. So both of our oxygens have 6 electrons. Okay. Now, here we have 16 total electrons. And carbon wants 8 electrons. And oxygen wants 8 electrons. And oxygen wants 8 electrons. So we need a total of like 24 electrons. Now look at this. Carbon has 4 electrons, right? And it wants 8 electrons in its valence shell. So it's going to have to share 4 electrons. That means it's going to have to share 2 electrons from this oxygen and 2 electrons from this oxygen. Right? So it's going to have to share 2 from each oxygen. This oxygen has 6 electrons in its valence shell, but it wants 8, so it needs 2 more. So it's going to have to share 2 from this carbon. Likewise, this oxygen is going to have to share 2 from this carbon as well. So carbon goes in the middle. Our first atom always goes in the middle. So carbon goes in the middle. We've got 2 oxygens on the outside. Okay, now carbon needed to share two, right? Carbon needs 8. So carbon has 4 of its own, but it needs to share 2 from this oxygen. So this oxygen is going to share 2 with the carbon. This oxygen, likewise, is also going to share 2 with the carbon. Now, this oxygen has 4 more bonding pairs. Now we actually put these at angles like this to kind of space them out nicely. This oxygen has 4 more lone pairs. Right, because this oxygen here shared 2 of its electrons with the carbon. And then it's got 4 more left, and they go as lone pairs. Now this carbon is going to share 2 of its electrons with this oxygen. This carbon is going to share 2 of its electrons with that oxygen. This is now a double bond. This oxygen and this carbon are double bonded together. There's 2 shared pairs of electrons between this oxygen and this carbon. There's 2 shared pairs of electrons between this carbon and this oxygen. And let's take a look at the valence shells. This carbon has access to all 8 of those electrons there. This oxygen has access to all 8 of these electrons here. And this oxygen has access to all 8 of these electrons here. So each one has a full valence shell. We draw this out in good form like this. COO dot 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 dot. Lone pair, lone pair, lone pair, lone pair. Or we would draw it like this. CO2, like that. I should have done this with methane. We would draw methane like this. Okay. Now let's look at nitrogen. Nitrogen, the chemical formula for nitrogen is N2. So there's 2 N's. And nitrogen, if we look here, has 7 electrons. 2 in the first shell, 5 in the valence shell. So each one has 5 electrons. 5 electrons. But each guy wants 8 electrons. So this nitrogen is going to need to borrow 3 electrons from this guy to get its valence shell full. And this nitrogen is going to have to borrow 3 from this guy to get its full valence shell. Right, so how does that look? We've got our one N right here. We've got our other N right here. The green guy is going to share 3 electrons with the purple guy. The purple guy is going to share 3 electrons with the green guy. Then the purple guy is going to have another lone pair. Do you see how the purple guy has 5 electrons here? 3 shared with the green guy. The green guy has 5 electrons here. So this green guy has access to 8 electrons in its valence shell. The purple guy also has access to 8 electrons in its valence shell. So we would write it, we would draw it like this, the Lewis dot diagram. N, 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. It's a triple bond. So it would be N triple bonded there. All right, this is how we do Lewis dot diagrams. They're complicated. We'll try to do a few more of them. There's some here that you can practice with. F2, NCl3, O2. F2 would look a little bit like this. O2 would look a little bit like this, but maybe not a triple bond. NCl3 would have an N in the middle with the 3 Cl's around them. All right, so that's molecular compounds and Lewis dot diagrams.